We're live. Okay, we did it. I'm distracted. I'm trying to verify this my Kindle so that I can buy Moya's book. And it's I see. Okay. All right. Anyway, talk amongst yourselves. You don't need me.
It's a pretty good book. I just finished reading it. So
yeah.
Oh, I need to get my hands on it. I have not yet acquired my copy.
It's on sale for $3.99 on Kindle.
Really?
Yeah. So why is my Kindle's not connected to my account anymore?
I love that this new computer allows me to jump over and actually just buy this thing, because that's what I'm doing right now.
Oh, cool.
Weird.
So, okay. I have now bought Moya's book. Thanks, Fraser.
Yeah. Everybody who's watching right now, if you want to buy Moya's book in advance for next week's show so that you're ready, it's only $3.99 if you want to get it on the Kindle.
She does the history about the Milky Way, but does it as the Milky Way tells the story. So it's kind of like part myth, part science. It's kind of interesting. Just the way she wrote it, I think that would be very hard to write it from that perspective, like the voice of the Milky Way.
Yeah.
Going through and explaining. And there's a lot of good hard science and astrophysics in it too. So.
Okay, I did it.
Yay!
I registered it. Okay, all right. Now I'm back. Now I'm fully operational. And I gotta switch to get the chat. Oh, recent. Oh, there it is. Yeah, install it.
Who thinks Starlink or Starship will launch before Artemis 1?
Nobody.
You don't think so? Because they're talking about doing a Starship launch next month, an orbital Starship launch.
Is that what they say?
I'm seeing on the schedule like late October, and right now.
Whose schedule?
On next space flight, usually they're pretty accurate as far as like keeping things updated.
So has Musk and team gotten a?
Oh, all the.
Yeah.
That I don't know. I know Artemis 1 isn't going till September 22nd or 27th.
27th is the new date.
At the earliest, yeah.
Yeah.
Probably October now. So.
Yeah. Yeah.
There's a difference between which one gets to orbit and which one takes off.
Yeah.
Right?
Yeah.
So it may not be the same.
Yeah. What is taking off? Like if you get an inch off the ground, have you taken off?
Have you won the race? I don't know.
Yeah.
Well, they haven't even. This one got down to a proper wet dress. They never got through the wet dress without fudging it a little bit earlier this year.
No, there were always exceptions.
Yeah, they always had to like fake out a computer or do something to get them down.
Oh, we got like 5 of the 8 things we wanted out of that. So, we're good. Yeah. We're solid. It's fine.
Our computer's sending us garbled data. We'll just tell the computer it's receiving good data. It'll be fine.
Just pull the circuit breaker or unscrew the light bulb and just keep going with the test. So.
Yeah, exactly. What could go wrong? Yeah. Oh, yeah.
Well, the last 2 launches were pretty much 2 more wet dress rehearsals. So.
So the feeling I have with Starship is just that it's not ready. That's all. It's just things have blown up. The Raptors are a brand new engine. There's every part of this is new and requires testing. And like Super Heavy is new. The Raptor 2 is new. They haven't been used together. There's just so much. And it just feels like there are steps that are missing that will come back to haunt them if they give it a shot. But if they just stack Super Heavy and put Starship on top of it and then hope that thing is going to do its job right the first time around, that's like the opposite of what NASA is doing with Artemis, right? Like, oh, we've got a little hydrogen that we detected in the atmosphere. Let's take a break. So, yeah. All right, let's get on with the show. Hello and welcome to the Weekly Space Hangout for Wednesday, September 14th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about a new satellite to be annoyed at, the hazards of uncontrolled re-entry, water worlds, stars stealing planets, James Webb overturning the Big Bang, question mark, and the laws of outer space. Joining me this week, we've got Beth Johnson. Hey, Beth.
Hey, Fraser. How's it going?
Good. Good to see you back. I get about like a month and a half now of saying hi to everybody for the first time after a hiatus. So I'm gonna really relish in it. We've got Dave Dickinson. Hey, Dave. Welcome back.
Hey, this is definitely our last show from this apartment here in Norfolk because we're out of here in 5 more sleeps.
Wow. And then where will we be?
We're heading over to Spain for a brief stint with them. I toward eventually moving over there. This time maybe over there for a week or so, but eventually we want to move over there for good.
I hope you found the internet's fine. I'm sure the internet in Spain is fine. It's better than here, right? Better than where you are.
It's okay. Oh, you know, our phones work over there actually with T-Mobile and stuff. I'm kind of excited.
Oh, okay.
I'm kind of excited with SpaceX's announcement about them partnering with T-Mobile and eventually providing Starlink directly. I think that's going to be kind of interesting. I hope that's the direction things go.
Yeah. Yeah, maybe my phone will finally work if that works with my Starlink connection. All right, and we've got Dr. Leah Jenks. Hey, Leah.
Hey, Fraser.
Welcome back.
It's good to be back. I feel like the summer just flew by.
Yeah. Yep. No, it didn't. It was awesome, but also I had a ton of work over the summer. Even though I take my hiatus, we were actually pretty busy around here. It's a lot of gardening, a lot of cutting down trees. It's good. All right. So before we get into this week's guest and news, I want to give a huge shout out to our good friends at the Weekly Space Hangout crew. They're our friends, our fans, our executive producers. If you want to join this amazing community, go to wshcrew.space. And if you're interested, I interviewed Nancy Graziano, cat herder in chief of the Weekly Space Hangout crew, on my podcast. So if you want to hear behind the scenes and understand the history of the Weekly Space Hangout and Nancy and the plans for the future, then you may want to check that out. Just search for the Universe Today podcast and you can find the interview that I did with Nancy. It was a lot of fun. All right, let's get into the special guest. We've got Dr. Paul Byrne. Hey, Paul.
Hey, Fraser. How's it going?
Good. So the question I always ask people, who are you? What do you do?
I'm a planetary geologist. That's kind of originally what I do. Now I do all kinds of stuff. But I'm also a self-professed Venus evangelical. And so you can usually find me on the street corner hollering at people about how 3 missions is great, but it's not enough. And we've got 40-year-old questions we need to study. And why is Mars get all the attention? I am genuinely interested in the processes that shape planets and what make them look the way they do. And a big thing that I'm interested in is a technique we call comparative planetology, which is basically taking one world and comparing it to others and seeing how they're similar and how they're different. So it's not so much focusing on one particular place, it's focusing on processes and see how they are common or how they're distinctive throughout the solar system.
Now, I've in the past said that Venus should just be pushed into the sun, but I can understand how you might want to compare it.
So that's what we would call a bad take.
Right.
If you're going to put something into the sun, you can put Mars in because it's a planetary embryo, right? Like, fine, whatever.
Yeah.
Really struggling to find it. Anyway, or Mercury. Now, I got to say, I have a special place in my heart for Mercury because I worked on NASA's Messenger mission, which was the first mission to orbit the innermost planet. And since most people have never even seen Mercury because it doesn't really ever get very high over the horizon, a lot of people don't particularly feel any kind of affinity for it. And I have heard referred to as burnt out cinder. I suppose if you really had to throw something in and you didn't want to spend a lot of energy in it, you could do that. But Venus, Venus is a fascinating world. Let me frame it this way to you, right? There are 2 Earth-sized worlds in the solar system, and one has squirrels and trees, and the other is the temperature of a self-cleaning oven and the pressure of a kilometer under the ocean. Pretty important to figure out why they're different, right? Because we're pointing telescopes to the planetary systems now. We're discovering more and more of these, and I should also kind of say, we're discovering more of these Earth-sized worlds, but we have not discovered an Earth-like world yet. And if someone tells you they have, they're lying. right? Because right now we can't tell if it's a Venus or an Earth or something else. So Venus is the key to figuring that out.
But it is really interesting. Like the solar system, the habitable zone of the solar system extends. It includes Venus, includes Earth, obviously, includes Mars, and yet we would not say that Venus and Mars are habitable.
Right.
What is the defining factor? What are the comparative geological features that have made Venus suck so badly?
Hey, so hang on a second. Okay, it doesn't suck. It's just different. Okay, I don't want to be Venus shaming here. Okay, so the shorter answer, we don't know, right? And this, in a way, this kind of points out the limitation of the phrase habitable zone, right? Because originally the idea of the habitable zone was that region around a star where Earth, with its present atmosphere and climate, would be able to sustain liquid water, right? So it really is only speaking about Earth, which means that it's not really applicable to anything else. For example, you could tractor beam Mercury into the habitable zone, and that won't automatically make it habitable. The biggest difference between Jupiter, Earth, and Venus, sorry, I posted about Jupiter on Twitter an hour ago, about Venus, Earth, and Mars is principally climate, actually. And the thing we're beginning to think about, by the way, I know you're only on for a while. I'm going to try and condense this, right? Because this is like a 4-hour Lord of the Rings style thing. So here's why Mars is different, right? So Mars has no present magnetic field. And that's often taken to indicate that Mars is unable to shield itself from the stripping effects of the solar wind, and that's how it's lost its atmosphere. And that's true, but it's probably not the full story. And in fact, recent work has shown that having a magnetic field might actually accelerate the loss of a planetary atmosphere, not retain it. The biggest reason why Mars is the way it is now is because it's small. And the way you replenish an atmosphere once it's stripped away by the solar wind is you have volcanic activity. And major volcanic activity on Mars ended a really long time ago. It turns out we know now that the amount of atmosphere that Mars, Earth, and Venus lose is about the same. But the reason that Earth still has an atmosphere, a meaningful atmosphere, and Venus has an atmosphere, is not to do with magnetic fields. It's to do with the ability to replenish it, because Venus does not have its own magnetic field, and yet its atmospheric pressure is 90 times Earth. So the reason Mars is different to those two is its size. Why Venus and Earth are different is a big question that we've yet to answer.
But then Venus being the same size as, roughly the same size in mass of Earth, and we've got the plate tectonics that are moving that regulate the temperature here on the planet and run the carbon cycle, and yet none of that seems to be the case on Venus. Do we know why yet?
So no, we don't. Although let me tell you, some of the work that I do in particular is actually focusing on looking at the features on the surface. And I think there's not plate tectonics on Venus, but there's something moving. And I think it's probably more than might have been recognized in the past. But what you don't get on Venus is a process that we call subduction, which is arguably the hallmark of plate tectonics on Earth, whereas the big tectonic plate dives into the planetary interior and in doing so draws out that carbon inside. We don't see evidence of that on large scales on Venus. One of the reasons why we think is probably because of a lack of an ocean. At least a leading model for how plate tectonics works is that the ocean water, where those plates subduct, helps to lubricate the plates and weaken the rock. It actually sustains plate tectonics. So if you did have oceans, then you've no plate tectonics. That so goes the thinking. Now here's the really interesting, well, there's many interesting things about Venus. Here's a really interesting thing about Venus. We learned in the 70s that Venus has lost a lot of water. It had way more water in the geological past. What we don't know is whether that water was steam and the planet was always a baking hellhole, or if it actually had liquid water on the surface. And recent modeling work in the last few years has shown that it's possible you can twist the dials in climate models to have Venus remain habitable, as in hospitable, clement, for as recently as 1 billion years ago. If you satisfy certain conditions, meaning for the first few billion years of the solar system's history, there could have been 2 large blue worlds, and they were similar. Wow. Now, under the assumption that you have largely the same conditions on both worlds, that it stands to reason you may have had plate tectonics. Right? You may even have had life. Per this model, some catastrophic climate change took place. And the most obvious explanation for that is widespread volcanism. It's possible that if, again, you twist the dials, you could have so much volcanism in such a short period of time that it would actually dump so much CO2 into the atmosphere that you would basically overwhelm plate tectonics and trigger a runaway greenhouse effect. That's scenario 1. Scenario 2 is that Venus was always hot, always hellish, simply by virtue of its proximity to the sun. And that's a really important thing to figure out, because as we start to discover more of these Earth-sized worlds, if we do find out that Venus is the way it is simply because of its distance to the sun, got a bit more sunlight through time, was never really able to cool down, lost water that was steam in its atmosphere, never approaching habitable conditions, then that makes it pretty straightforward for us to say that if we find a large world close to its star, it's probably like Venus. If we determine, though, that Venus at some point did spend part of its life like Earth, then that raises two questions. One, how do we identify an Earth from a Venus orbiting with a star? And why did Venus change? Or why didn't Earth? And that's a really important question for understanding the conditions that give rise to planets like our own.
How do you think about the field of exoplanetary science when we're having such a hard time studying the planets that are right next door to us?
Yeah.
You know, like, is there phosphine discovered in the atmosphere of Venus? Maybe, maybe not. Let's find out. And it is still a controversy among astronomers whether this signal's even there, and if it is there, what it means for life and so on. And that it's right there. It's like right next door. And then you compare that to the exoplanets that are turning up. And the amount of just unknowns that we're going to be saddled with for hundreds of years, probably, kind of boggles the mind, literally, until we can send a spacecraft to land and you know, lick rocks. Right. Where we actually know what's going on these worlds.
Right. And, you know, we may never get spacecraft to these planetary systems. If we don't develop some sort of superluminal technology, we are restricted to tens of thousands of years flight. And it becomes very difficult to imagine scientists being able to, building a probe that would last that long. So, yeah, arguably, we are stuck at where we are. Here, there's a couple of really important things exoplanets give us. And one of the things that I'm particularly interested in is the geology of exoplanets, about which we have virtually no information. So, you know, it's pin, you know, head of a needle, right? That's the information we have, and then we extrapolate and start to make some educated statements. The one massively valuable thing that exoplanets, one of the many, that exoplanet surveys and exoplanet science does, is gives us a much broader canvas from which to look and see what's out there. That's extremely valuable, because it's likely, at least I'm of the opinion, that the types of processes, the sheer number of them, the ways they're manifest, the different kinds of planets you can get, we see in the solar system a pretty small portion of that much broader canvas. Yeah. And although we consider these worlds, so for example, the phosphine thing, that is testable. We could, I don't know if the Da Vinci probe, which the NASA selected 3 missions for, well, it's selected for 2, and then the European Space Agency is doing 1. Yeah. They may be able
the Rocket Lab one as well.
Oh, well, I mean, the Rocket Lab one. Now, the Rocket Lab one won't, I don't think, tackle phosphine, but because it's going to be too high where it's doing its sampling, but it's definitely part of the building up the kind of set of spacecraft. So we could go and say fly a balloon through the Venus clouds. That's one of the ways we would tackle the phosphine question. We do not have the option for the foreseeable future to test this for an exoplanet, which is why I don't think we're going to be, overall, we're probably not going to be able to answer that many specific questions about specific exoplanets. There are probably a few we'll spend a lot of time on, but in the main, we will probably be limited to understanding things at a very large scale. But that's invaluable because, for example, we're learning that there is this so-called Fulton gap, right? Or there's the radius gap between large super-Earths or rocky worlds, we think, and then these small mini-Neptunes or sub-Neptunes, relatively small gas giants or ice giants. Although ice giant, that's a whole other thing, by the way, because there could be a large Earth-sized object inside Uranus and Neptune and we don't know, in which case ice giant's not a good name for them. But the point is, it's that surveying we're getting. And that becomes extremely valuable in being able to say what kinds of things are out there. What do we have in the solar system that's representative, and what do we have that's not? So that's really where we're going to make some really dramatic discoveries in the coming years, particularly now that Webb has been commissioned, is online, and is starting to send us atmospheric data from those worlds.
I mean, the shame is that we're discovering the outliers. We're discovering the weird stuff, the hot Jupiters, the super Neptunes, the super Earths, and we're not getting a really proper distribution, a comparative geology, as it were, of the different kinds of planets that are out there. Are there projects in the works that kind of you're excited about that could give you some of those answers?
So I get excited about a lot of stuff. So yeah, and I really cannot wait to see what Webb gives us. There are next generation telescopes that have been proposed, like HabEx or LUVOIR, that could potentially start to target smaller worlds. And you're right, we are more likely to know about the outliers, the ones that are big, that are obvious, that are easy to detect by virtue of the detection methods we have available to us. Even then, we're still learning some useful stuff, for example. So I had a paper that was published late last year where we extrapolated in an educated way, right? Which is not to say that we were making a particular, although we actually did make some predictions. of course, the biggest thing about science is if you come up, you have to predict something, right? You've got to propose something that's testable, otherwise it's not science, right? So we try and make some sort of set of measurements you could make. But one of the things that we were interested in is what conditions govern how rigid the outer part of a planet is, because that plays a big role in understanding whether or not it might remotely have the chance of having plate tectonics, for example. And so what we were able to do is take what we know of the solar system and extrapolate out to conditions that we do not see in the solar system in terms of planetary mass or surface temperature or distance to the sun. Right? We have a rough idea of how rocks behave under different pressure temperature conditions, so we can again tweak the dials and the models, the knobs, and basically come up with this kind of realm where we think there could be a certain kind of world that we could test for. So one of the things we determined was that we called it an eggshell planet. It's a large rocky world that is a function of a bunch of different reasons. The actual brittle layer of rock is either extremely thin or absent completely. And the rock would behave in a weird way in response to things like impacts. And that would make it extraordinarily difficult for it to have plate tectonics. And thus it would have a really hard time drawing carbon into the interior, even if the rocks are made of silicon like they are on Earth. One of the predictions of this is that if you pointed a very powerful telescope at these worlds, you'd expect to find a carbon dioxide dominated atmosphere like Venus is, for example. Now, there's a few ways you get that atmosphere, that composition. But one of the ways is you would not be able to draw the CO2 down just like you don't in Venus, and that it would be consistent with so-called these eggshell planets. So we're trying to make predictions about the kinds of geology you get. We are so far off being able to say that these things have continents or mountains, but you can begin to think about these kinds of questions going forward.
I mean, I think about like what would a rogue planet look like out in the cold of space? Would it have active hydrology? Would there be cryovolcanoes going on and radioactive heating? I think about like these Hycean worlds, these hydrogen-rich ocean worlds, even just regular ocean worlds. Like the realm of possibilities kind of staggers the imagination. And I would love to know whether it does fall into all these weird, bizarre worlds that are pushing the boundaries across all the different types of planets are possible, or in fact do they all settle into terrestrial planets, gas giants, ice giants? That's it.
I mean, so here's the thing. I don't know the answer, but I don't see any reason why you couldn't have those. I can't think of any thermodynamic reason. Like, so for example, we have no true water worlds in this planetary system. We have these ocean worlds, which is a kind of a catchy phrase to describe these icy satellites, some of which are huge, that have big, deep oceans. But if it's not that hard to imagine a scenario where you have an Earth-sized world that is completely covered in water. And by any measure, that's an ocean world. Now, if you have one of these that a rogue planet, for example, it's likely it would be a giant version of Ganymede or Europa, right? It would have a frozen outer interior. But for a world as big as Earth, and I think we see the same in the geology of Venus, these worlds last a long time. The heat energy inside them. I mean, right now, if you dig down a few meters in the ground, after you get away from the diurnal effects of the sun, which heats the ground, you get down a few meters to the point where the sun has no impact on the temperature of the rock. About half the heat you detect comes from the decay of radiogenic elements in the mantle, and about half of that heat comes from the formation of the planet itself. It's accretional heat energy. It's still there. And it's hot enough that the outer core is liquid, and it's iron, right? You need high temperatures for that. So if you were to, again, if you're familiar with Q from Star Trek, right, that asshole, if you were to snap your fingers and you were to cue Earth out into deep space, sure, it would freeze over and everything on the surface would die and it would be blah, blah, blah. But the hydrothermal systems, there's no reason they wouldn't keep going because they'd be shielded. So the point is that I don't see why you can't have a vibrant geology on a world that isn't orbiting a sun. It just depends on how big. The bigger you are, the better, right? Because a small world like Mercury or Mars or the Moon, they really will cool down pretty fast. And we see that. The big worlds, they can retain their heat for a very long time.
Yeah, super interesting. Well, Paul, we could have this conversation all day, and later on I think we should. But you're going to stick around for the rest of the evening. But let people know how they can find out more information about you and where to find your work.
Sure. So I'm on Twitter a lot because I procrastinate a lot.
I mean, I've got to say, you have one of my favorite Twitter accounts out there, and you and we've talked many times in the past. But if you haven't already, follow the Twitter feed that you're about to hear.
So I tweet on @theplanetaryguy, and I do it for fun. I reach out I try and let folks know what's happening in the solar system. I'm a professor at Washington University, and one of the things, my favorite things to do is to teach courses to students who may not know this stuff that well, to just share with them some of the wonder and I know you all have about understanding the cosmos around us. So you can follow me on @theplanetaryguy on Twitter, or if you need to email me, you can Google me. It'll come pretty good.
Yeah. And what I love about your feed is that you give context that comes out of left field, which is really helpful. So you're often sharing stuff that are the questions that answers to the questions that we had that nobody seems to want to offer up that additional information, and it's really great. And you'll go on these tangents and go down these rabbit holes and talk about some of these topics we talked about tonight, and it's terrific. So you should definitely follow Paul's Twitter. All right, you're gonna stick around. We're going to move on to the news portion, and feel free again to jump in as we go. Beth, let's talk about stars stealing Jupiter-sized planets.
Okay, so this headline actually the press release caught my eye because they labeled it as planetary heist, and I'm rather than Q, I'm sort of having that Ocean's 11 vibe from the headline of all right, let's get together and steal a planet. Yeah. But in this case, what's happening is you have young planetary systems in working their way around younger stars in star-forming regions that are fairly close together. And there are massive stars that are sort of mixed in there, and they have a tendency to gravitationally perturb these young systems and basically steal Jupiter-sized planets away, which is one possible theory for why these planets end up orbiting very far out from their sun, where they were not likely to form. And when they say way out from their sun, their stars, it's hundreds of times the distance of the sun to the Earth. So several, 100 AU rather than, we're not even talking close in. It's pretty far out there. And so it looks like they're actually like pulling these planets off of their systems at an early stage. The best part in this is that there is a backronym that is just so tortured, but it's fantastic and I love it. So the study is called the B-Star Exoplanet Abundance Study, and they have acronymed this to BEAST, and they are referring to the planets they are studying as beasties.
Now the stars themselves, if I recall, they're like A stars, so they're much more massive and hot than the sun. Yeah, and the planets are not close, so they're right at the limits of gravity and being able to grab them. How do they have a sense like how common this is? Is this happening all the time, or is this just like it can happen?
It can happen. They basically used computer simulations to sort of run these, and they're, again, because of the acronym is they are B stars, not A stars, but still very massive. And so they're saying that it occurs on average once in the first 10 million years of the evolution of a star forming region. So it's not
of the whole region.
Of the whole region. So it's not a really common thing that happens, but it is one possibility for how these planets get shifted and end up farther away from stars.
Right. Got it. Very interesting. Paul, do you have an opinion on this? Do you have a question?
Well, so this just goes to there's actually something that occurred to me that we don't really have a good handle of generally, which is the evolution of planets through time. And very often we'll think about a planet and we know now in the last 15 years or so the planets migrate, they change their position, or at least they can early on as the solar system settles down. We think that happened to the giant planets. But the idea of something forming in one system and then being captured by a star someplace else means that if you go and try and figure out what the atmosphere composition is and does that tell you anything about this parent star, that actually might not be worth your time because it doesn't come from there. And we do not have a good handle on how planets can evolve and what happens to the different stars. And it's a really important thing. So if this is true and this is really what's happening, that just makes our job so much harder. But that's okay. But like, geez.
Like if it wasn't already hard enough.
Yeah, right.
Yeah. So like planets, not even able to know if the planets came from the same star system. But one in a star-forming region, that's not much. There's plenty of room. All right, Dave Dickinson, let's talk about an upcoming Has it already launched?
It already launched last week. We're still trying to hunt it down.
Okay. So this is BlueWalker 3. What's the deal?
Yes. This was an interesting passenger that caught a lot of our attention that was on the last Starlink launch last weekend. This is from a company called AST Space Mobile, and they want to put up 110 of these. They're about 8 meters in diameter, 24 feet across. And for context, this is about, I was trying to think of another satellite that was as bright as Echo 1 back in the 60s. You might remember NASA put out this big inflatable reflective balloon that was about a little bigger than this BlueWalker 3 satellite, and that came down to about, at a zenith pass, at about as bright as Sirius, -1 magnitude. So this hasn't, as far as I've seen, unfolded yet. I've been looking at and trying to contact the company on their Twitter account. They haven't. It deployed with a batch of 60 Starlink satellites, so we're still trying to sort out the actual ID of this satellite in that batch. And U.S. Space Track hasn't put out a confirmed ID on it. So we've been trying to, all us people in the satellite tracking community have been trying to hunt this down, but there's a lot of interest as far as how bright this is going to be. The ISS, the International Space Station, it comes down to about magnitude -3 or -4. It's quite bright when it goes on an overhead pass. This isn't quite that big, but you can imagine if there's 110 of these moving around. Incidentally, what these are, they're testing, similar to what SpaceX announced recently, they want to do a T-Mobile. They want to do a direct 2.5 gigahertz connection with cell phones and satellites in orbit, so that you won't have to have a Starlink terminal or antenna anymore. That's where the technology, even SpaceX wants to go this way eventually. That Starlink will just be an app on your phone that you connect to, and your phone will talk directly to the satellite. Which, my opinion on Starlink, I always have gone on record saying it's nuanced, because I'm excited if I can have a high-speed Starlink connection and stream from remote Morocco. But, of course, I think there should be some oversight as far as I don't want to see a sky where there's more artificial stars than real ones moving around. But, light pollution's been a thing long before Starlink, too. So it's I think there needs to be some kind of oversight putting out these kind of bright satellites, because OneWeb wants to put up satellites, Starlink wants to put up, I think the FCC, SpaceX has got an approval for 30,000 satellites eventually in their constellation, which is quite a lot. There's a Starlink launch tonight. They've been having an amazing amount of launches this year. Yeah. There's almost a Starlink launch either from Vandenberg to Cape or Kennedy Space Center, like every once or twice a week. So
I think aren't they shooting for like 60 this year and 100 launches next year or something? I mean, it's if they get Starship going, Starship can launch an exponentially larger amount. They want to do perhaps, I believe it's over 100 per launch on Starship. If they start putting that up, that's going to be like putting them out there like Pez dispensers pretty soon. So that's
the new Starlink, the one that's going to be the version 2.0 that's going to offer the satellite connectivity, they're going to be much bigger, much beefier. Like what's the visual magnitude of the Starlinks right now? It's like what, 7?
They're down to 6 or 7 when they're put in their orbital slots. Now, when they go initially, they're naked eye. And we wrote an article about that. I believe it was Universe Today this summer as well, that the newer Starlinks don't have visors on them because they're using the line of sight laser communication between the satellites, which the visors interfere with. So the observers have been noticing that they're once again brighter than they were, even when they're in their operational slots. They're about 2 magnitudes. The International Astronomical Association put out that the goal target, I believe, is 9th magnitude. They want to get them down to. They're still about 2 magnitudes brighter than that. Now, what I think is going to happen is, and amateur astronomers have been doing this with astrophotography for years, is that we're going to have some kind of automated AI technology that will look at images and simply identify Starlink streaks and take them out. Like I said, astrophotographers have been doing that already with photographs. Like satellite streaks are very characteristic in how they appear. So that's, I think, where the technology is going to have to go. Because things like Vera Rubin, when they go online, that goes down to like 29th magnitude, I believe. It'll see plenty of Starlinks.
Yeah. Well, and I'm using Starlink right now, so I'm obviously in the pocket of Big Musk, but I should be cutting off my account in another month or two, as soon as my fiber optic cable is run and installed. But it'd be interesting to see.
They're doing great things, like in Ukraine, keeping they've kept the internet on there basically through the entire war.
So, do we know what the brightness? I mean, you said people have been trying to find it. Is it just that they haven't deployed this thing yet, and so we haven't been able to see it, or what?
I don't think they've deployed it yet. I've been kind of monitoring their account, AST Space Mobile. I haven't seen any announcement that they've deployed it, and I haven't seen any other satellite watchers or trackers put out anything saying that. I think it's probably going to be around 0 magnitude on the zenith pass eventually, if it's as bright as other, like I said, Echo 1 was the one that I used for context in the article. I was trying to think of what other satellite was possibly about this size before. So, but I'm still tracking it at Astro Guys. As soon as I see a space track ID and I start seeing reports of whether they've deployed it or unfolded it, we're going to be putting out there how bright it appears.
Yeah, I mean, like the Starlinks, like people always worried that they're going to lose the night sky as the Starlinks launch, but you can't see them. Like you can't see them with the unaided eye. But magnitude 0, if there's a bunch of those in the sky, you will absolutely see them. That's ridiculously bright.
And I always say the best thing that amateur astronomers and satellite trackers can do is chronicle what you're seeing. Is put out there if we're seeing Starlinks that are brighter, put out there and start reporting what you see out there. Basically, is the best thing we can do is chronicle what's going on.
Yeah. I mean, I actually, this question came up in my question show this week, and I gave about a 20-minute, very nuanced opinion about Starlink. The gist being, if the goal is to connect the other half of humanity to the internet, that is a noble goal, and I would gladly give up the work of all astronomers, since I have that ability, to connect humanity to the internet. But put up or shut up. Like if you say that's what you're going to do, then there's got to be laws. There's got to be penalties if you don't, because if you're just letting bankers trade faster from their yachts, then that is not a price I'm willing to pay. And so show me when people in remote villages in Africa are getting access to the internet and they're able to receive health information, and their kids are able to attend virtual college, and they're able to get bank accounts and do business. And if you don't deliver that, then you lose your internet. Yeah.
Then tonight's Starlink launch was actually canceled for weather. So.
Oh, well, there you go. But yeah, so that's it. And so I think it's just like the horse is out of the barn, right? There was a chance to regulate these companies, to get them to agree to terms about how the good of humanity would be improved. Yeah. And that conversation was never had, and their feet were never held to the fire, to the level, because this is a common good. This is a tragedy of the commons. And now we're paying the price, losing the sky without getting the connectivity of all humanity that we were promised. And that's the part that pisses me off. All right, let's move on. Leah, tell me about how the James Webb is, you say James Webb's first glimpses of early galaxies could break cosmology. Break it?
Yes. So we're not breaking the Big Bang yet.
All right.
Not yet. But basically, as hopefully everybody has seen the pictures of JWST's galaxy fields, these beautiful pictures compared to Hubble. And astronomers expected that with JWST, we were going to be able to see much further back into our cosmic history and see much older galaxies. But what this article is talking about is basically that nobody expected how quickly and how many of these old galaxies we were actually able to see. So, for example, with Hubble, before James Webb, the oldest galaxy, or the furthest galaxy away that we could see with Hubble, was at redshifts of 11, which is about 400 million years after the Big Bang. And it was thought that that was kind of right at the precipice of when we expect galaxy formation to happen in the cosmic evolutionary history. But what astronomers are finding with JWST is that we are not only going way further back, but we're seeing galaxies that are much further developed than what we would previously have expected. So, for example, the first galaxy that kind of set all this off was at a redshift of 13, which is about 300 million years post-Big Bang, so almost 100 million years earlier than what we previously thought. And then there have been many by the GLASS and the SEERS surveys that are redshifts like 16 up to 20, just really ridiculously far back. I think redshift 20 is like 160 million years post-Big Bang, so very, very early. And what they're finding is that these galaxies, you expect if you're looking back that far and that old, you're going to see something very, very faint and, you know, you're not going to be able to see it that well. But what they're finding is that these galaxies are actually looking a lot brighter than they would have expected. And then, like, furthermore, there was one at redshift 10, I believe, that apparently has Milky Way, basically looks like the Milky Way. And that is very, very old. And so this kind of, all these observations are basically disrupting our preconceived notions and theories about the evolutionary history of the universe and how and when galaxies form. So there are a lot of different reasons that this might be happening. There could be looking at dust. There could, of course, always be, you know, analysis issues. But if these are all real and we're really seeing these, it may lead us to need to modify our standard cosmological model, so our lambda CDM cosmology, which is exciting.
So what could be some possible explanations? When you say you want to modify the lambda CDM, what would that mean?
Well, so basically what this would mean is that when we have, like, for example, you can, there are very famous dark matter simulations that show if you fill a box of dark matter, you have overdensities and underdensities, and eventually these kind of clump together to form galaxies. And so you could imagine that, you know, you have there's something in our standard model about the very early universe and how dark matter works, for example, that could be incorrect or need to be modified somehow. People definitely like to talk about MOND in this context, modified Newtonian gravity and ignoring dark matter. So I don't know about that, but that's an option. So there's a lot of exciting work that I think to be done, looking at what could potentially be going on here, looking at the physics of galaxy evolution.
But essentially, you're looking for some mechanism that is pulling the galaxies together more quickly than the original models were anticipating. I mean, we sort of imagine this buildup of tiny little, I guess, stars being collected into dwarf galaxies, the dwarf galaxies merging into larger galaxies, and eventually you get something that's more substantial. It spins up, you get those spiral arms, and from what I understand, the going theory was that these galaxies sort of built up in connection with their supermassive black holes.
Mm-hmm.
Is it possible that, like, would primordial black holes solve this? Because you could sort of start with these anchor building blocks of galaxies?
I think probably primordial black holes would be not large enough to have a huge effect. But I suppose it's possible if you had enough of them, maybe in the early universe, and then they, for example, combine, and that's kind of what seeds these supermassive black holes way earlier than we would have thought. That would be possible. So yeah, I think there's a lot of different directions you could look at for this.
So I guess what observations, what data will astronomers cosmologists be looking for to help decide or try and figure out what is actually going on here?
Yeah, so first of all, they need to make sure that these distances that they're calibrating to all of these galaxies are actually correct. It's very hard to determine a precise distance when you're talking about this kind of range. So I think that gathering more and more data as we get more observations from JWST and seeing that we're confirming that we are actually seeing galaxies at these particular redshifts, and it's not just some sort of mistake in the analysis pipeline, that will be really important. And then I think, using other types of surveys to kind of corroborate and look at other galaxies closer to us to maybe learn a little bit more about their evolutionary history.
And back to that comment you said that it's dust, that, it's always dust, right? It's always dust ends up being the thing that makes your science, affects your science. And so if it does turn out to be dust, then actually those galaxies are not as redshifted. Like the dust is contributing to their redshift, and actually they're not as far as we think they are. And it makes perfect sense for them to be as mature as they are. Is that right?
Right. So that is one of the explanations. But apparently the ALMA telescope has done some observations of these regions and found that they're not particularly dust heavy. So that is a possibility, but apparently is not super likely. So it's looking good for it being the actual observations, but you can never totally be sure.
Paul, if you could use James Webb to see the geology of an exoplanet a couple of 100 million years after the Big Bang.
So I'm thinking of what this is like. So we know that when you have low metallicity stars, you're probably not going to get a lot more than helium and hydrogen. So I don't know. I don't think we know when terrestrial planets become easier to make, right? Because you need those heavier elements to make the minerals that go into making rocks. But I've got to think that somewhere is a planet that is extraordinarily old. And I just would love to know what it's like to stand on the surface of that world and see a young universe around you. What would that look like?
Yeah. Everything would be so much denser than it is today. I mean, you could find one of there's like that Methuselah star. There's like stars in the Milky Way that are as old as the universe itself, or almost as old. And so you could theoretically find the one of those stars with the oldest planet on it, and you could at least get a sense of what the first planets might have looked like. Right.
I mean, certainly we do know that there are some exoplanets that have, because identifying the age of a star is extremely challenging, but there are exoplanets in the catalog that we think orbit stars that might be of order 11 billion years old, under the assumption that the planet is about the same age as the planetary system. Even going back 2 billion years since the onset of the Big Bang, it would still be incredible to know what a world. Just what's a planet look like that's that old? Mm-hmm. We have no idea the answer to that question. What does it look like? What are the processes going on, if any? Is it just a big, boring, dull old Mars-looking thing, or is there still active geology? Is there weather? But to think about what the night sky would look like on those worlds just blows my mind. And I'm content to accept I'll never know, but it's something I'd like to think about.
Yeah. You could have a star that is that long-lived. I mean, something that's less massive than the sun could easily be still around from that time. And assuming that the metallicity, would the metallicity of the star give you a hint at the chance of planets? Have they found an association?
That's yes and no. The answer is largely no, because nature doesn't care for what we want to know.
Yeah.
It's very hard to be sure that, because on Grow,
that'd be so easy.
Right, wouldn't it be easy? Yeah. So on Grow, if you look at the composition of a planet's rate around a star, you should be able to say something about the stars, absent other processes. I mean, what I've come to realize is that all planets are concentrated chemical engines. They take in stuff and they change it. But you can try to back out what they had originally. But I don't think we have a great understanding of looking at a star's metallicity to be able to work out what that means for the kinds of inventories of planets. It might just mean that there's fewer of them, or they're smaller, or it's equivalent to a Kuiper belt is smaller. We don't know. But certainly, I can't imagine that you didn't have planets forming as soon as the first stars started to form. They may largely be giant planets, but maybe locally they had enough rock and ice to make icy satellites. I would love to know what that first generation of planets orbiting those first population 3 stars would have looked like.
And to get even weirder, you think about the times when the universe was warmer, like within the first few million years of after the Big Bang, the entire universe was room temperature.
Right. Yeah. And you know what we now know from looking at other planetary systems, the planets form really fast. Within a few tens of millions of years, you have a bona fide planet.
Yeah.
Sure, there's lots more that has to happen internally for it to sort of really get going. But you could potentially have formed clumps of matter that would form things we might call planets within the first few tens of millions of years of the universe's life.
At a time when the entire universe was habitable. What was the habitable zone? The answer is yes.
Everywhere. Yeah.
Everywhere.
Yeah, and then things slowly settled into worlds or something, And of course the sky was a different color. I mean, it's wild to think that it was so different to what we're used to now.
Yeah. All right, let's move on. Beth. Water worlds, hiding water underground.
Speaking of populations, I guess that's kind of one of those things you have to question. As Paul said earlier, we don't have something that we would consider a water world here, but we have found evidence that we have all these icy moons that have water under the surface, these subsurface oceans. So what's happened here is that a team of scientists basically took measurements for 43 different but similar exoplanets and looked for patterns. And they used both the transit method and to get the diameter of the planet, and then they used radial velocity to find the mass, and then they basically calculated the density and went through, and the pattern that they found was that these 43 worlds are too light to be made entirely of rock. So but they're also very close in, so it's unlikely that the water would be on the surface, so it's probably underneath the surface in the rock somehow. And we're looking at another potential group of subsurface ocean planets with, a lot of water.
Explain that. It's a weird idea because we don't see that here in the solar system, or I guess we don't know if we do, but you've got Earth, the water's on the top. You've got the ice moons, Europa and Enceladus, water on the top. The water seems to float on top of rock. Do they propose a mechanism for how that much water could be sequestered inside a planet?
Not that I saw in the article. One of the things that they were talking about was that if there was water on the surface, which, because these are planets that are going around red dwarfs, so these are M-type stars, and they're close in, but that means that if they were that close in and the water was on the surface, we would see that sort of puff up on the diameter. So you'd get sort of like supercritical gases, and the radius measurements that they got, they're just not matching what they're expecting to see from that. So they're not giving a mechanism for it, but I think a lot of it is simply it's just too hot for it to be on the surface. So
but like Earth is too close. I mean, if Earth didn't have an atmosphere and a magnetosphere, we would lose our oceans to space. And so the answer is we're protected by a magnetosphere. So I wonder if that's a possibility, that it isn't underground, it's just protected. This sounds like a Paul question.
Yeah.
Well, so
Paul,
it is worth pointing out that 98% of Earth's water is in the mantle, right? Only 2% on the surface. It's locked in hydroxyl molecules in the mantle. So technically speaking, Earth isn't a water world, or it's got a thin scum, a little thin layer of water. Right? I mean, if aliens were looking at Earth, they were looking at the mantle, right? They're not looking at the oceans. That's just a thin layer on the outside, a film.
98%. I had no idea.
Yeah, the mantle's full of hydrated. Yeah, or they're basically hydroxyl molecules locked into mineral lattices, which is why, for example, you can have water-rich volcanism taking place 4.5 billion years after the planet forms. Most of that water will never escape. but it's how Earth and probably Venus can replenish their atmospheres. Yeah, I mean, so I bet this is spot on. The atmosphere would expand, it would basically volatilize under those temperatures, even with the magnetic field. It would look like Venus, right? You might hang on to the water, although even close to an M star, an M-class star, you're probably going to have a lot of what's called photodissociation, where you'll break that water into its component hydrogen and oxygen in the atmosphere. But at the same time, there are other ways you get relatively low density values with low radius measurements. And one option might be that you have a relatively low density material. Maybe there's not a lot of iron in those minerals. And so if you do have rock, it's just not all that dense. Or you even have a highly fractured body that the overall porosity is quite high. This is, I think, a really nice example of, albeit limited to very limited data with radius and mass measurements, you can begin to at least extrapolate wildly. And of course, the nice thing is it's hard for someone to prove you wrong.
Yeah. We'll wait for the extremely large telescope to
right in the 2090s. So, I'm saying
exactly. For you to counter my paper, we'll see if you live long enough.
Exactly.
Old man. Yeah. All right, Dave. We're out of time. Dave, let's talk about uncontrolled reentries.
Yeah, this was an interesting study last month out of the University of British Columbia, looking at the troubling trend it was kind of highlighting of larger mass rocket bodies just coming in an uncontrolled manner, and the fact that a lot of what they call the global south, like a lot of southern hemisphere countries, share a disproportionately higher amount of risk than the northern countries that launch all these satellites. The only launch facility south of the equator actually is in New Zealand right now, is Rocket Lab out of New Zealand. Even the one in French Guiana, I believe, is above the equator. But most of the countries launching are China, Russia, United States, and everything. Of course, satellites all pass over equatorial regions at some point. And so it's more likely that the space debris is going to re-enter over some of these countries down on the southern equator. Now, two high-profile re-entries we had in the last year, and one was this summer. China is building their Tiangong space station, and their rocket boosters, which are quite large, are coming in just on uncontrolled reentries. I mean, no one has been injured by these yet, but these are the biggest reentries since Mir and the Salyut space station, and everybody remembers the hysteria around Skylab back in the 70s. I mean, China's not totally to blame. There's a lot of reentries. There was some space debris from SpaceX from the when the Crew Dragon capsule comes in, they typically jettison the trunk of the spacecraft, and sometimes pieces of that have made it down to Earth. And a lot of the Soyuz boosters, that they come down just somewhere along the path of the International Space Station after they launch Progress. And those are fairly large too, but the Chinese boosters are kind of exponentially large. And what's kind of troubling is there's not really anything out there. The UN has some statements out there about countries need to be responsible for what they put out there in low Earth orbit, but there's nothing really holding them to it to say that there needs to be a method to have the boosters re-enter after launch or some kind of drag sail. There's ideas out there to do these kind of things, to put satellites down after they're, we talked about how many satellite launches are going to be going up in the next decade or so. This is all exponentially going to add to the load of space debris that's out there in low Earth orbit. So there needs to be a way to bring these things down in a controlled manner at the end of their life, either drag sails, re-entry, retro rockets. Incidentally, China's launching another module for their space station next month. So we're probably going to see another uncontrolled re-entry that we're all going to be tracking. The core station for the Tianhi module, when it went up, that passed right over. It re-entered in the Indian Ocean, but when we were all tracking it, this was last year, it passed over several large cities in the Middle East minutes before it re-entered. So that easily could have been a much more disastrous situation.
Yeah. I mean, ironically, it feels like the lower you go, the better it is for everybody to have these satellites at Starlink levels, 300 kilometers. I'm trying to remember what Starlink's at.
They're in low Earth orbit.
But even below the space station, right?
Yeah.
And so these things are auto cleaning themselves up. If you don't continuously boost it, this thing is re-entering the atmosphere shortly. Yeah. But if the thing is big, like the science module from the space station, then it's going to drop on somebody's head, and you need to take responsibility for that.
Yeah,
And that's the part that
they get atmospheric drag, and as the solar cycle, we're going towards solar max right now too. We're going to see more reentries because that puffs up the outer exo atmosphere of the Earth, and that increases the drag on these satellites. There was a batch of Starlinks earlier this year that was lost to a solar flare right after. We're seeing Starlinks already come in now, so they're just kind of replacing them by attrition as they go up now. So.
And did they lost the whole batch?
Just about. Some of them are still re-entering, but it was in February of this year. Yeah, I wrote an article about it. It was there was a solar flare that went off right after they launched, and it would just happen to hit that window as they were deploying, and they virtually lost that batch.
That's
amazing. I think there were like 15 that survived, and the rest got fried.
Us folks like Jonathan McDowell and Marco Langroic, and we're all tracking these things on space track as soon as they come up, and we all noticed some very low perigees for those satellites, and we kind of had a hunch there was something wrong with that batch, and then SpaceX announced that they lost that batch.
I feel obligated here to step in and say that at Venus you wouldn't have this issue because that thick atmosphere, actually there are no craters smaller than 3 kilometers in diameter at Venus because the atmosphere shields the surface. So if you really did have to drop big things in, you could just direct them over there, no problem, and they wouldn't cause a problem for anybody.
Yeah, landing on Venus is easy.
Yeah, right? You don't land, you fall, right? So like when the Soviets sent their stuff in the 70s and the 80s, the way you come in is you come in on a parachute until about 60 kilometers, then you drop the chute and you just fall. It's closer to dropping something off the side of a research ship onto the ocean floor than it is the standard, what we might think of, say, for Mars in terms of how we get to the surface.
It's weird that the Soviets had better luck with Venus than Mars.
Well, Mars eats spacecraft for breakfast. Mars is,
it's
like
easier.
The worst of all
it's easier to get to Venus, and it's closer, and there are more frequent launch windows. It's a big Mars. It's just done such a good job in the last 25 years, marketing wise. Venus is easier.
Yeah. All right, Leah, we've got like 1 minute. Tell me about outer space not being the Wild West.
Yeah, so this is actually very related to Dave, what you're talking about with the space debris. But basically, as Dave also mentioned, their space is international territory, and there are some UN treaties about it, but it's very unclear who's in charge, kind of what the framework is for how you're supposed to conduct yourself in space. And so McGill University and partner universities in I think like 6 different countries have spent the last 6 years making this manual on use of space for military and peaceful purposes that basically looks at international law and has distilled how it applies to space for 52 specific rules that covers things like space debris and liability and nuclear tests in space and putting military bases on the moon and all of this stuff that as more and more countries get involved in space programs and these issues come up, hopefully will be helpful to provide a little bit more clarity and guidance and providing some regulation about these things, of which there is currently very little. So that is, I think, a positive step forward.
Can confirm. I mean, it's funny. People always ask me, like, what are you going to do when people want to go and live on Mars, and can they mine Mars and so on and so forth? And it's just like all this stuff is covered in many cases by the Outer Space Treaty. They're very clear. Like if people want to violate the Outer Space Treaty, they can do so, but the rules are pretty straightforward about this. You can't own it. You can't. It's for science. It's for the planet. It's for humanity. And I think, maybe the Outer Space Treaty needs some updates, but this stuff was all sorted out back in the 60s.
Yeah.
And sorted out well, I think.
Fun
yeah.
fact,
what's that, Dave?
Look up, fun fact, we as in the United States, tested nuclear weapons in space before the Outer Space Treaty. Like 1960, it's Operation Starfish Prime. It's on YouTube. It's very bizarre to watch. but they actually detonated a nuclear weapon in space over the South Pacific. And they could see it from Hawaii. It was pretty wild.
Didn't that like knock out a bunch of electricity transformer stations in Hawaii?
Yes, it knocked out a few satellites, I believe, too. Yeah, they did it right before the Outer Space Treaty went into effect, but we have detonated a nuke in space.
That's amazing.
Kind of scary to watch, actually.
Yeah. Seeing a nuke go off in space overhead. I mean, that's definitely gives you an understanding that someone has the ability to end your civilization should they want to, which is why they signed the Outer Space Treaty. Anyway, well, we're reaching the end of our hour, so it's time to wrap things up. So, Beth, what are you working on, and where can people find out more?
I am prepping for a big SETI Talks event. We will be doing SETI Talks live. It's a kind of SETI Talks, SETI Live combination for the DART impact on September 26th. So we will have a whole bunch of scientists coming by to talk to us and tell us about the mission and their science and all of that. So looking forward to it.
That's awesome. That sounds great. And if people want to find out more?
I am at Planetary Pan pretty much everywhere, and you can find SETI at SETI Institute.
Perfect. All right. Leah.
Yeah, so I just moved to Chicago and started a postdoc here. So I've been thinking a lot about black holes and gravitational waves and dark matter and all that fun stuff, and eating a lot of deep dish pizza.
How is the pizza there? Must be amazing.
I love deep dish pizza. It's great. I'm a big fan. But yeah, and you can find me on Twitter at Leah G. Jenks, and also my website, leahjenks.com.
Fantastic. Dave.
Frequent contributor, Universe Today, Sky and Telescope, and I still have my first book from a few years ago. And I have my second book, which is strange to think now this is 2 years ago this came out. So it's I'm due to write another book. So
it's time.
It's time. It's every other year is about a good pace for book writing.
And Paul, you were willing to stick around for the shenanigans, so I'll give you a second chance for people to find out more about you and where they can go. So, what's the best place to keep track of you?
Sure. So you can find me on Twitter. I am at The Planetary Guy. I blog and tweet about all kinds of stuff. And right now I'm involved in some pretty exciting Venus stuff, which I'll be talking about on Twitter soon. So stay tuned.
There you go. That sounds amazing. All right. And of course, I'm Universe Today at all the things. Thank you to everyone for watching us tonight, both on YouTube and on Twitch. Thanks to all the moderators. Special thanks to Nancy Graziano. Again, reminder, if you want to hear an interview with Nancy Graziano, check out my podcast, Universe Today podcast. You can hear her philosophy and how she herds the cats. It's a really fun conversation. And there's going to be one coming up with Dave Dickinson, too. And we have moved, so people are wondering what's happening with Astronomy Cast. We've got a new episode of Astronomy Cast coming out on Thursday, so bear with us. Pamela's been having some neck pain, and it's not me. I'm not the pain in her neck. It's apparently actual physical pain, but hopefully we're going to get to a point where she's not currently in a lot of agony while we do the show, which makes sense. So that is probably going to be tomorrow, but maybe it'll be delayed again. We'll see what happens. All right. Again, thank you everyone for watching. Really appreciate it. Thanks for a special guest, my co-hosts, and we will see all of you next week. Thanks, everyone.